see the second experiment under 7th one, that is verification of Norton theorem. So aim in application. So verification of Norton theorem to find Ix through AB if a load resistance of 10 ohm is connected across it. Let's move to theoretical calculations. As we are aware, we have two steps under Norton theorem or Thevenin theorem, and this comes under type 2 problems. So step 1, we will find VTH or VAB or VOC. Step 2, we will find IAB or ISC, right? So we can call this as ISC. So under Norton theorem, what we'll do is we'll call IAB as IN, right? Now to find VOC, open it across AB. So let's solve this by mesh analysis. So when you apply KVL in this mesh to find current I, this is our equation. But before that, what exactly is this VAB? We need to unbox what exactly is this VAB. So this VAB is nothing but voltage drop across this 50K. So I can write voltage drop across 50K based on the current ATI as I1 into 50K in this mesh. So then it would be I1 is nothing but minus ATI. So this ATI is going in anti-clockwise, but we have assumed current I1 in clockwise direction, thus we have incorporated negative symbol. So thus when I substitute I1 the above equation, I get VAB as minus 4 mega into I. So M stands for 10 power 6 into current I. So to find VAB, it's simple. It is I have to find the current I. So when you apply KVL from my first mesh, this is my equation, 8000 I plus VAB by 1000 minus 2000 minus 2. So VAB we have solved, it is nothing but minus 4 into 10 power 6 into I. So when I substitute that, what do I get? I get the value of I as 0.5 milliamperes. And when I substitute this 0.5 milliamperes above, I get VAB as minus 2000 volt. Now VAB is minus 2000 volt. It is nothing but voltage up across 50K or voltage up across these two terminals VAB. Now second step to find ISC or to find IAB. So on a Norton theorem, it's better that we use instead of IAB as IN. So short circuit, I'll always find the current going down, and you can see what am I doing here. Why am I eliminating 50K? Now you can see that these two branches, that is, this is your first branch and second branch, they appear as if are they in series, parallel or star delta. They are in parallel, and this resistance is actually a 0 ohm. So then I can say 50K is parallel with 0 ohm, thus I have to, what is the answer actually? 50K into 0 divided by 50K plus 0, it is actually 0. That means the 50K is not adding any value to the circuit when I short circuit to find IN. Okay, so then what we can do here is we can neglect your 50 kilo ohm. But where is VTH? VTH is nothing but it is across 50K, that is plus here and negative here, right? It's across ATI or across this wire. So VTH across a wire having a 0 resistance. What is voltage? You know, voltage is I into R. When R is 0, right, whatever is the value of current, your voltage drop will be 0. Thus VAB would go towards 0. As VAB is 0, what will happen to 0 by 1000? So 0 by 1000 is again 0. And how do we neglect voltage source? Or when voltage source is 0, how it behaves? When voltage is 0, let me ask you a question. When current is 0, what is the circuit? Open or closed circuit? When current is 0, that means it is open. And when voltage is 0, that means it is short circuited. So VAB, that is 0 by 1000, it becomes as a short circuited circuit. So this is a reduced circuit to find IN. Now let's apply mesh. It's quite easy. Now we know I1 is nothing but minus ATI, and we know IN is nothing but I1. So I1 is, as I told, I1 is minus AT into I. As ATI is going in anti-clockwise, I1 you have taken in clockwise, thus you are writing I1 as minus ATI. And when you apply KVL for mesh 1, the equation is quite simple. It's 0.25 milliamperes. Right? Substitute this I1 at the top in the equation. You get, substitute the value of this I here right? And we get the answer for I1 or IN, which is nothing but minus 20 milliamperes, right? Now, what is your Norton theorem, right? So Norton theorem says, as similar to Thevenin theorem, it is replaced by any two-terminal network can be replaced by one single equivalent current source parallel with its resistance, right? And the value of Rn is nothing but Vth by Sc or VAB by IN. That is nothing but its ratio of voltage and current at the terminal. Thus, you get the value of Rn as 1100 kilo ohms. Now, to find Ix through AB, now I hope you understand that the orientation of IN, right? Now IN we have found going from A to B, right? So what will be the orientation of IN in the circle that I have marked here? I have found the current going A to B, thus the current has to be in upward direction for IN. Now from this circuit, by current divider, one can find the value of current as minus 19.998 or approximately minus 20 milliampere. So the value of current that is asked in the question is here, right? That is nothing but approximately we can say that as minus 20 milliamperes. Now let's move on to the circuit connections. So you can see here we need one VDC, we need 1, 2, 3. This is third resistance of 10 ohm, third resistance of 10 ohm, and then we need two dependent source. One is F and one is E. We have already seen in the previous experiment under Thevenin theorem that this part name is E and this part name will be F, which is nothing but current dependent current source, and E is voltage dependent voltage source. So let's move on to simulation. So what all part names we require? We need one VDC was connected here, and we need one we had a resistance connected here, right? And we also had a resistance of let me rotate this and place this here, and we had a part name E, which is voltage dependent voltage source, and we have one more part name F, current dependent current source, and we need one common ground, that is E, G and D. Yes, so let's go back and check if these were only components required. Let us connect them now. Now you can see the circle in the voltage dependent voltage source, the one which is in the rhombus or the one which is in the circle, that's your actual voltage source, right? So let us connect that. Now similarly, the one which is in your rhombus or one which is in circle, that's your actual current source. Right, let us first value them and then we'll see how do we connect the other parameters. So this was 50k and this was 10 ohm, and then this was 2 volt, this was 8k. Now what is your gain here? Your gain is not 1 and it is neither 1 by 1000. As I told, we are substitute it in decimal points. So what is 1 by 1000? So instead of substituting 1 by 1000, calculate what is the value of 1 by 1000. That is nothing but 0.001, right? So substitute, just recheck whether you have done that. Yes, we have done that. Next, what's your gain for your current dependent current source? The gain is 80. So double click on your current dependent current source, gain by default is 1, revalue that to 80. Click on enter or save attribute and then OK. Now, how do we connect your dependent voltage first? So your VAB is a dependent voltage that's connected where in the circuit, if you can remember, it was across 50k, right? So positive connected to 50k above and negative is connected to 50k below. Now this current I, if you can remember, is connected here, right, in this orientation. The same orientation has to be maintained when you are connecting. So what I'll do, I'll delete this wire here, right, and this arrow mark should synchronize with the orientation shown here. So let's just see how do we connect. So in a sense, the current will flow through the dependent parameter. Yes, the IMAC is synchronizing, and then it goes through 8K. Now let's connect your gain, your common ground, and make sure these two at the bottom, they are connected. Okay. Now, so what we have found, let's find the current. Let's save the file. Now, as is a DC circuit, I just enable transients, save the file, and then let us simulate to check our answers. Yes, you can see that without toggle cursor, it's landing on the exact value minus 20 milliamperes, right? Or you can see it's approximately minus 19.998, the same thing that we have got in our theoretical calculations. Now, as we need to verify, so this is the best practice actually, right? So kindly, in a copy pasting the element, kindly delete all your markers, right? So let us copy this and verify for your VOC, right? This is your main circuit, so I'll copy paste it twice. So what I'll do is I'll just type here as main circuit, and this one is for your this one is to find VOC or VAB. Next in here, and this was to find here Norton current IN. Okay, now, so how do we find your VOC? As we know, we should not delete 10 ohm, and when we simulate, we get an error. So let us keep, when the just the characteristics of your voltmeter, it has high impedance. So let us revalue this as large as possible, and let us revalue for current as least as possible. Okay, so instead of 10 to find current, let us keep this as 0.00001 m, very least value. Yeah, I'll leave it here. Right, now after doing this, let us keep the marker. For voltage we take marker voltage differential, and you have to remember how we have found. We have found such a way that top was positive and bottom was negative, and similarly for the current marker, it is going downwards, and here also this is your load current going downwards. So R2 will rename this as load, and I'm finding voltage here. I'll rename this as VOC or VAB, anything, and this was your Norton current IN, right? So let me try to simulate now, and first let me save and then simulate this file. Yes, you can see my VOC is minus 2.00K, which is nothing but minus 2000 volts, and IN is exactly minus 20 milli, and we're getting the same, and the load current that we have seen earlier is minus 19.998. But if you observe keenly, first I have found out what is my the load current, and from there on, from that circuit, yes, so from the main circuit, then I have copied. So once your circuit is correct, then you can copy paste to verify for your two parameters, that is VTH and ISC, or VOC and IN. Okay, then let us try to build your Norton equivalent. Norton equivalent, we need one IDC. So if we take, instead of we don't have one part name for IDC, let us type the part name as IDC, and if you remember, the current is going to upward direction, and we need two resistances, and both would be appearing in parallel. This is your RN and this is your load resistance, right? And this is, what is the value of IN? The value of IN was minus 20 milliamperes, and the load resistance, sorry, your Norton equivalent, what is the value of Norton equivalent? Your IN is going upwards minus 20 milliamperes, and RN is 100K, IX was 10, and then we still get the answer as -19.998 milliamperes. So let's try to build a Norton equivalent here to verify the answer. So this was 100k and this was 10 ohm. Let's build the circuit. You have to give common ground, do not miss this, and then your current marker going downwards. Okay, so your load and R11 both should be same, right? So your load and R11 both should be same, you can see here, right? Thus we have verified our Norton theorem. So without applying any theorems or any logic, just for the given circuit, when you simulate, we found the current that is as that we found the current that as I load. We've got that as -9.998, and this is by Norton theorem, and this is for your verification of Norton theorem for IN, and this is your verification of Norton voltage or open circuit voltage VOC, that is -2000 volt, right? So this is how one has to solve and simulate and find out the answers for your Norton equivalent. So we have seen how do we connect, we have simulated, we have discussed on the results. Thank you.